This PowerPoint is over integration. So integration effectively is going to be the area for a curve with an x and a y. So ordinarily when we do an area, we can use a graph kind of like this. We can actually split it into parts where we can take geometrically what the area is going to be. So for here, let's say we take the interval from 2 to 6. So we basically make the bounds from 2 to 6, and then we break it into shapes that we can deal with. So we got a triangle here and a rectangle here. The area of the triangle is going to be equal to 4, and then the area of that rectangle is going to be equal to 12. Now the total area is going to be both of those added together, which is 4 plus 12, and that gives us 16. So that area, we could actually use some integration as well, which is what we're going to be getting to, but effectively it's taking the area of this in order to figure out what the integral is. Next example, we have what looks like a semicircle here as well as a straight line, and we need to take the area from 0 to 9. So then we break it off into shapes that we can deal with. So we got effectively 1/4 of a circle right here, then we got a rectangle, triangle, and this triangle that is below the x-axis is going to be a negative area. So figuring out each one of these, that half circle is going to be 1/4 of pi r squared, and that's going to be equal to 4 pi. The rectangle at the bottom is going to be equal to 8. The triangle is going to be equal to 9, and then that triangle that goes below the x-axis is going to be equal to -4. So when we add all of these together, we get a total of 4 pi plus 13. Now, if we have more of a shape that is a little bit more, a little bit harder to come up with a geometric shape for it, then that's where we start getting into integration. So let's say we need to go from 2 to 6, but I don't really have the area of a shape that's kind of curved like that. So what we're going to do is we're going to split it into 8 equal parts. So from 2 to 6, 8 equal parts would be half each. So essentially with that, we're going to divide it into 8 separate parts with a width of half on the x, and we're going to basically make triangles, and this is going to be the lower sum. So essentially we're going to look at half of a width, and then we're going to take the y value when it gets up to that height, and then the width, and then add or multiply those together in order to get the total area for that section. And then we keep going across the entire graph all the way up until we get our 8 portions. And you can see here that these 8, when we add them all together, we're going to get an area that is going to be something a little bit less than what the area is for the actual graph, because you see there's little pieces missing here. So we can actually do the area a different way as well. So let's take the area with the upper sum. So that means that the height is going to go up until it actually hits it on the right-hand side here. And you can see we actually have a little bit more area than we did before, because now we're a little bit over the graph. So then when we add all those together, we get an upper value for that area. So essentially what integration does, what calculus does, is it takes that upper area and that lower area and kind of squeezes it and make smaller and smaller intervals until you can actually get the actual area as the width of each one of those little pieces approach 0, which means the number of areas is going to be infinite. So we have the upper area here that we're going to be adding all together, and then we got the lower areas that we add all together. So then that means that our actual area is going to be somewhere between 6.146 and 6.424. And if you integrate a cube root of a function, then from 2 to 6, you're actually going to get an area of 6.287, which you can see is in between those two values. So this is what brings us to what we call antiderivatives. Now we have a derivative, we know what the functions are for derivatives, for the power rule, for chain rule, and all of those things. Then we're going to go in reverse in order to get what we call the antiderivative. So derivative is going to be the function that takes the slope, and then the antiderivative undoes that original function. So we could think of it as like kind of an inverse operation. So if you divide by 2, you can inverse that by multiplying by 2. If you subtract 1, the inverse of that is going to be adding 1. So the antiderivative is the inverse of a derivative. So the function that we use, let's say we have a function when we have antiderivative, and this is more so for your math class if you go into calculus, you just use a capital F to say that you've taken the derivative or the integral of that function, also called the antiderivative. So let's say we have this function right here, 2x to the third. Now, if you remember when we did the operation in order to take an inverse function, essentially we would undo what we did. We would do the opposite of what we did in order to get that original function. So the power rule multiplies the coefficient of the power and then subtracts 1 from the power. So we bring down the exponent and multiply the 2 by the 3 and get 6, and then we subtract 1 from the exponent and we get x squared. But when we take the antiderivative, we go in reverse. So instead of subtracting 1 from the power, we're going to add 1 to the power. And instead of multiplying by the coefficient, we're going to divide by the coefficient to get the new power. So for here we have 2x to the third. So the first thing we're going to do is we're going to add 1 to that exponent, which gives us 4. And then from there, we're going to divide by 4, so 2 divided by 4 gives me 1/2. So then this is going to be my integral function. Now there is a possibility that I could have several integral functions. If I take the derivative of any one of these, I get this original function here, because when I add or subtract a constant, that constant doesn't change, so the derivative gives me 0. So what we have to do is we have to account for the possibility of some other value, some constant that's going to be added on there. So when we take the integral, we're going to add c onto that. So for this, let's say we take the derivative of this function. We're actually going to rearrange this so we can get what the notation looks like for an integral. So just like finding the opposite or the inverse for a function, we're going to take the dx over to the other side to get to our original function, and then we take the integral by using the integral sign. The integral sign is basically an elongated s. Because what we're doing is we're actually taking small little changes in y and then adding them all together, which is what a summation is. So instead of using that summation where we take essentially that summation all the way to 0 or infinity, then we're going to integrate using that. All right, so our original function is going to be equal to the integral of f of x dx. That little part right there is called the integrand, and this part over here is called the variable of integration. And then that's where we get our function, where f of x plus c, just in case we have a constant. So an indefinite integral is what we call our antiderivative. So we know the power rule. Reverse the power rule, we're going to add 1 to the exponent and then divide by that exponent. For the chain rule, we also have a reverse operation for that as well. We call that u substitution. So essentially what we have is, if we have this function right here and we take the derivative, then we get dy is going to be equal to cosine of x cubed, and then take the derivative of the inside, which is going to be 3x squared, and then we get dx on the other side. Now if we need to go in reverse, what we do is essentially we have this inside x to the third. That's going to be our u, and that's what we're going to substitute. But then the dx also has to be substituted, because if we substitute x with u, then we got to substitute dx with du. So our u is going to be equal to x to the third, so du is going to be equal to 3x squared dx. That's the derivative of this. So in our original function, we're going to replace x cubed with u, and we're going to replace 3x squared dx with du. And then we're going to integrate like we did before. And when you integrate your cosine, integral of cosine is going to get you back to sine, and then you have your plus c. So then I got sine of u, and I've already taken the integral of u. That u we're going to plug back into our original function, the x to the third goes back in there. So here are some examples of u substitution with some functions. So here we have the square root of 9 minus x squared, and then multiplied by negative 2x dx. So sometimes the u substitution is pretty obvious. We're going to make the 9 minus x squared equal to our function of u, and then the du is going to be the derivative, that's going to be 0. And then we have negative x squared, so then that's going to be 2x, negative 2x, and then we got the dx there. So in our function, we're going to replace that 9 minus x squared with the u, and then the du, and then we have the square root is the same as to the power of 1/2. So now when we integrate, we're going to add 1 to the exponent. Adding 1 to the exponent is 2 halves, so that's going to be 3 halves when I add, and then divide by that exponent, which is 2 over 3. And then we're going to plug back in our original function, which is 9 minus x squared, which we have 3 to the third power divided by 2, so that's going to be square root to the third power, and then when we plug that in, this is going to be our original our function of integration. Notice here we add c when we have an indefinite integral. We don't know what range to integrate over. The next function we have, our u is going to be this 1 plus x cubed, or I'm sorry, x to the fourth, 1 plus x to the fourth, and then the du is going to be the derivative of that, so it's going to be 0 plus, bring that 4 down and subtract 1 from the exponent, it's going to be 4x to the third. Now you notice here I don't have a 4, but I have a 4 here, so what I'm going to do is I'm actually going to bring this 4 over to the other side, and then the x cubed dx I'm going to replace with 1/4 du. All right, so then that 1/4 is a constant, so it comes out of the integral, and I have 1 over x squared because that original function was squared, which means it's going to be u to the -2 power. So I'm going to add 1 to the exponent, which gives me -1, and then we divide by -1, so it brings a negative out front, and I got the plus c on here. And then u to the -1 puts u in the denominator, and then we can go ahead and plug back in our u as 1 plus x to the fourth, and then we have that plus c on the end. The next function here, we have 9 minus x, and then we have a square root of x. Well, this one we don't necessarily need. We have like what looks like separate functions, and part of it is the u and part of it is the du on each one of these, but that doesn't mean that we have to do a u substitution. So for here, we can actually distribute that x squared to both of these, which means x, the square root of x. So that means x is to the 1/2, and then when we have an x times a square root of x, that gives me 3/2 x. So now we can basically just take the integral of each one of these separate terms. So we add 1 to the exponent, that's going to be 3/2, and then we divide by 3/2, which means we multiply by 2/3. And then the second term is going to be adding 1 to the exponent, which is going to be 5/2, and then we divide by that, it's going to be 2/5, and don't forget that negative in there. So then we got 9 times 2 over 3, so it's going to give me 6, and then the to the 3/2, the halves is going to give me a square root, so square root of x cubed, and then we subtract that 2/5 x to the square root of x to the 5th plus c. All right, last example here, I have x divided by 2. That's going to be part of the sine function. So x over 2 is going to be our u, and then 1/2 dx is going to be our du, but I don't have a 1/2. I actually have an 8, so I kind of have to manipulate this a little bit. So I'm going to bring this 2 over to the other side, and dx is going to be equal to 2 times du. So then I put in my u, and then I have 2 times du, 2 times 8 gives me 16. So bring that 16 out front, and then take the integral. Integral of sine is going to be negative cosine, and then from here I can go ahead and plug my u back into the function, and this gives me my function as negative 16 cosine of x over 2 plus c. Next thing we're going to talk about is definite integrals, meaning that if I have an actual interval that I'm going to be integrating over from a to b on the x-axis, then I can use this notation in order to figure out what that actual number is. So up to this point, we've only come up with the values in the equations. So let's use this notation in order to figure out what the actual area is going to be. So the area is bounded between a and b, like we've done before in the previous examples at the beginning of this PowerPoint. And then the area below the x-axis is negative, area above the x-axis is going to be positive. And then the fundamental theory of calculus, and this kind of gets back to the fact that the integral is the antiderivative, because if I take the rate of change, which is the derivative, and then I take the integral, then what I get is I get the total change. So I'll get back to the original function where I have the upper value plugged into the original function and the lower value plugged into the original function. So taking an integral of a derivative, I get back to the original function with that change. Keep in mind that the integral is the area from the a to b, that's on the x direction, and then the y goes from the x-axis, which is y equals 0, up to the function or down to the function, depending on if it's above or below the x-axis. So another theorem of calculus is the average value theorem. So if you have an area of a function, then if you want to get the average, you can use this value right here. So if we have the integral, that's the area, the total amount, the total change that you have, that area is going to be equal to some average value times the x there. So essentially what we're doing is we're taking some weird function that has a weird shape and we're turning it into a rectangle where this is the x and this is the y. So that average value is that average y value for this entire function. So let's say we have a function like this and we're going to find the area, then we're going to take the integral of that. Now there is some value right here, right in the middle. If we know anything about averages, then that means an average value has some above and some below. So if we take take a function where we have a basically make a rectangle out of this, we can actually see that some values on the y-axis or on the function itself are going to be equal. Those y values are equal to the average. So that same amount, we basically take the area, and here we get the same area. If these two areas are equal to each other, then that means the function at C, so at any one of these values, is equal to the average value of the entire function.